Okay, let's get started. So if you recall, we're talking about singularities. Singularities, and what we had just finished with last time was Riemann's theorem on removable singularities. So Riemann's theorem on removable singularities. Does anybody remember what that tells us? What did that tell us? Like, when do you have a removable singularity? You remember? Yeah. Go ahead. No.
Like if our function is bounded near the singularity?
Basically, yeah. Right? As long as you can find, if this is your singularity, you can find some disk in which it's bounded, then it's a removable singularity. Right? Okay. So today we're going to start off with a characterization of what happens near poles. So it's a corollary. So again, you start off with f, a holomorphic function that has an isolated with an isolated singularity. At a point. Has an isolated singularity at a point. Then f has a pole. F has a pole there, if and only if the absolute value tends to infinity as z approaches z naught. Okay. So, right. Okay. So the proof is pretty straightforward. So what's a pole again? Can anybody remind us of what the definition of a pole is? Right. So f as a pole means what? Yeah, go ahead, Jason.
F is 1 over gz for some function g that has a 0 the pole. But it's not exactly 1 over gz, it's 1 over gz everywhere else except for that.
Yes, yes. So f has a pole. F having a pole there means that that if you look at this function, f of 1 over z, then you can extend that to a holomorphic function. You can extend that to a holomorphic function at that point by defining it as at 0 there, right? So right.
F of 1 over z or 1 over f of z?
I'm sorry, f of 1 over z. I'm sorry, 1 over f of z. Thank you. Okay, so okay, so going forwards, right? F has a pole at z, right? So if f has a pole at z naught, well, that means that, of course, that 1 over f is holomorphic. With a 0 at z naught, right? And of course, that means that the absolute value of f of z is going to go to infinity, right? So the absolute value of f of z is going to go to infinity as z goes to z naught, right? Because your holomorphic with a 0 there, right? So your values are going to get arbitrarily close to 0. So 1 over that is going to get arbitrarily large, right? Of course. Okay, so that's the easy direction, right? That's the easy part. The other direction's also pretty straightforward, right? If f over z goes to infinity as z goes to z naught, well then of course 1 over f is 1 over f is holomorphic and bounded near Z0. Right? And we just said that if you're holomorphic and bounded, then you've got a removable singularity. So, right? So 1 over f has a removable singularity. At Z0, and takes the value 0 there. Right. But that's what it means. That's the same thing as saying that f has a pole there. Okay, so that's pretty straightforward. Yeah, Jake.
Could you also argue in the forward direction that if f was bounded near Z0, then the singularity would be removable and therefore not a pole?
Let me think for a second. So if f is bounded, but you don't know, this thing not going to infinity, it doesn't necessarily. See, this is a little bit different from no. So no, yeah, it's not quite the same thing. So no. Yes.
How do we know that 1 over f is holomorphic from that?
Well, f is holomorphic, right? And you know that it stays away from 0 as you go off towards as you go to here, right? So 1 over f is well defined, right? It's the only thing you're worrying about is if the denominator gets to 0, but this is going to infinity, right? So yeah, it can't be 0. Other questions? Okay. So we've characterized removable singularities, and we've characterized poles, right? And any other singularity is called an essential singularity. So the last type of singularity are the essential singularities, right? So basically, an essential singularity means that it's any singularity that's not removable or a pole is called essential. Okay, called an essential singularity. And the very cool theorem describing how functions behave near essential singularities is the theorem of Casorati-Weierstrass. So here we go. And this also is maybe considered a consequence of Riemann's theorem, Casorati-Weierstrass. Okay. So if f is holomorphic in some punctured disk around a point, and Z0 an essential singularity of f, then the image of f on that disk is dense in C. The image of that disk, so this is my notation, this is a pretty common notation. This is the image of f on this set. Right? It's the collection of all f of z where z lies in that set. What? That's weird, yeah. Yeah. But if you looked, it's actually even stranger than that. There's a theorem of Picard which says that, in fact, the image is not just dense in C, but hits all of C except for maybe one point. So it has to hit every point in C infinitely many times, except for possibly one point. Yes?
So is an example of an essential singularity like 1 over z at z equals 0?
That's a pole. That's a pole,
Okay.
right?
Oh, I see.
That's a pole because, right, as you go close to it, you know, the size of it goes to infinity. Yeah. The example that they give in the text is this one: e to the 1 over z at 0. At z equals 0.
Okay.
Right. So like as you approach on the real axis here, you go to positive infinity. Right. As you approach on the negative real axis, you go to 0. Right. And as you approach on the imaginary axis, you just spin around. Right. So it's it's not removable. It's not a pole. It's an essential singularity. Okay. Okay. So let's do this. So suppose we'll do it by contradiction. Suppose that the image is not dense. Suppose the image is not dense in C. Okay. In other words, there's going to be some bad point, which we call W. Yeah. Which we call W, where there's a neighborhood around it that F does not map into. Okay. So the image does not intersect this neighborhood of W. So there's a bad point. There exists this point W in C, and a radius such that a radius delta such that if you take any point in our disk, then it doesn't lie in that. It doesn't lie in there. The distance from the image to W is greater than delta. Okay, so everybody, you know, here's our disk. Everybody in here gets mapped outside of there. Okay. Now, if that's true, then we can create a function. So create a function g of z as 1 over f of z minus w. Okay, this is well defined, right? Because we're never gonna hit w, right, on our disk. Okay. So what's the point that this function is bounded, right? So observe that g of z is smaller than 1 over delta, right? Because all those distances are bigger than delta, right? So it's a bounded function. So it's right, bounded on that disk. And it's holomorphic, right? And it's holomorphic there, right? Because the denominator is never 0, and f is holomorphic, right? So you've got this bounded, you've got a holomorphic function that's bounded on a disk, bounded on a punctured neighborhood, and so that tells you that z naught is a removable singularity. So there are two possibilities. One, suppose that the value, suppose you remove the singularity and you give it some value, right? So suppose that the value you give it is non-zero, right? But in that case, this is holomorphic with a non-zero value there. So that tells you that f of z naught minus w is going to be 1 over gz naught, right? Right. And so right. And so what does that tell you? That f would be holomorphic, would then be extendable to a holomorphic function at z naught. Right? In other words, z naught is not an essential singularity contradiction. Right? Everybody okay? Right? Okay, so that's, and then the other possibility is that this thing is 0. But in that case, f of z minus w has a pole at z naught, right? Which would mean that z naught would be a pole for f, and then again that's a contradiction. You guys, is that okay? Right. Right, because 1 over this would be a holomorphic function that has the value 0 there. So this thing has a pole that tells you that f has a pole there, right? And so that's a contradiction also. Okay. So that's it. Yes.
So does this theorem kind of tell us that like around an essential singularity we'll always see weird oscillating behavior?
Yeah, you see some sort of craziness happens at an essential singularity. Yeah. Yeah, I did. Yeah. Yes. Okay. So. So that basically concludes the sort of characterizations of the behaviors near singularities. Right? There's 3 kinds of singularities. Singularities, removable, where the function has to be bounded nearby. There's poles where the function's modulus must go to infinity nearby. And then there's essential singularities where the function has to attain every single value nearby. Basically. So we're going to sort of switch gears at this point somewhat and talk about meromorphic functions on the extended complex plane. So, meromorphic functions on the extended complex plane. So the plane union infinity. Okay, so start off with something called stereographic projection. So stereographic projection is a way of projecting the plane onto a sphere. So you take the complex plane, right? and then you place a sphere, a unit sphere at the origin. Place a unit sphere at the origin, and then you define a map from the plane to the sphere, or from the sphere to the plane, it doesn't really matter, by saying that you call the north pole n, and you say every point on the sphere will be every point on the plane will be identified with a point on the sphere, the one that you get by taking a ray from the north pole through that point, and you see where it intersects the sphere. Okay, so so that gives you a bijection between the sphere minus the north pole and the complex plane. Okay, and that projection is called stereographic projection. Okay, so you get this bijective map. It actually has a lot of nice properties. Yeah, there's one mathematician, I forget, there's like a mathematician artist who has used a 3D printer to print out like patterns on the plane projected onto the sphere. So you can buy copies of the sphere, and then if you put a light source here, then it like creates all these like tilings and patterns on the plane. So just like taking advantage of this mathematical knowledge for profit. Okay, so that gives you this map from the plane to the sphere, but excluding the north pole. Okay, that's this map is called stereographic projection. Okay, and then you think, well, as you get farther and farther out in the complex plane, right, as you head off, farther and farther away from the origin, well, the points that you get are going to be higher and higher on the sphere, right? Right. So as you go farther off in any direction, the values that you get are going to go higher and higher on the sphere. Okay. And so it makes sense to call this not the North Pole, but rather infinity. Okay. So we call that pole, that thing infinity, and then the sphere includes infinity, and infinity is just one of these other points on the sphere. Okay, so this S is called the one point compactification of the complex plane. Right, aka the Riemann sphere. Okay, so what is infinity? In complex analysis, infinity is something very concrete. It's the North Pole on the sphere, on the Riemann sphere. Okay, so we'll talk for a moment about singularities at infinity. So suppose you have a function that's defined, outside of some disk. Okay, so you have some disk of radius r, right? And your function is defined outside of there, right? In other words, it's defined on you have some slice of your sphere, and it's defined above that slice. And suppose it's holomorphic, then consider f of z being big capital F being little f of 1 over z, right? That's going to be defined on, that will be defined on z less than 1 over r, right? Excluding 0, right? And it may have some singularities, right? Where the function, where the original function is 0. So if f if that thing has a pole at 0, we say little f has a pole at infinity. Okay, right? Or if it has an essential singularity at 0, we say it has an essential singularity at infinity, et cetera, et cetera. So essential singularity. If it has a removable singularity at 0, then we say it's removable singularity at infinity. So, basically we just invert the variable. So, and then if you have a function that's meromorphic, and has, at worst, a pole at infinity, then we say f is meromorphic on the extended complex plane. Okay. And the main thing we're going to do here, we're just going to have one result here, which is that those functions are the rational functions. So those meromorphic functions, those functions are simply the rational functions. Okay. Yeah, Connie.
What does it mean, like, by at worst, a pole at infinity? Does that mean not an essential singularity?
Right.
Okay.
Yeah. So either a removable or a pole, removable
see.
singularity or a pole.
But that doesn't have anything to do with poles elsewhere. Like there can be poles not at infinity.
Yeah.
Yeah. So you've got a meromorphic function. So it has poles. It has poles in the finite plane.
Okay.
Right, in the regular complex plane, and if it doesn't have an essential singularity at infinity, then we say it's meromorphic on the extended complex plane. Right, the extended complex plane being C with infinity. Okay. Okay. Yeah, this is not the most exciting thing, so but it'll get better shortly. I promise you. Okay. So proof. Right. Say F is meromorphic. Say F is meromorphic in the extended complex plane. Okay. So it may have a removable singularity infinity, or it may have a pole at infinity. Okay. So what did that tell you? That tells you that f of 1 over z. If we look at f of 1 over z, well, it either has either, by definition, this has either a pole or removable singularity at 0. Okay. Okay. So, right. But what does that tell you? That tells you if you look at the original function, then that is holomorphic. In some large disk. Right, in some large disk centered at the origin. Right, does that make sense? Like, so you have your your function has a pole or removable singularity at 0, right? So, right. So that tells you that it doesn't. There's a punctured neighborhood around here where you don't, where you're holomorphic, or maybe it might well be the full neighborhood in which you're holomorphic, right? But in which this function is holomorphic. So if you're looking at f of z, well, that means that you're holomorphic outside of the inversion of this disk, right? So, right, this function is good in the punctured disk of radius 1 over r, right? So this function is good, is good outside of the
F is holomorphic for z such that 1 over z is in the disk.
Yeah, right. So it's good outside of there, right?
Yeah.
Right. It's good outside of this. Sorry, I should say it's good outside of there. And so, sorry. Yeah. So it's holomorphic in. Sorry. So this guy is holomorphic in some punctured d sub r around 0, right? And so this guy is holomorphic in for z bigger than 1 over r, right? Right. So what does that tell you? That if there are any poles, excluding the pole at infinity, if there are poles, they all lie inside of this disk, right? They all lie inside of this bounded disk, right? So F has, at most, finitely many poles. Right, because if it had infinitely many poles inside of the 1 over r disk, then they would have an accumulation point, and that would not be a pole, right? That would violate the function being meromorphic. Okay. So let's call them z1 through zn, and one of them may be infinity. Okay. So okay. So now what we do is we're just going to subtract off the parts that give the poles. So So for each finite pole, write f of z as fkz plus gkz. So for each finite pole z sub k, write f of z as these two parts, where this is the principal part, and this is the holomorphic guy, right? The non-vanishing holomorphic function nearby. I'm sorry, the holomorphic function. Right. Okay, so right, this is a polynomial in 1 over z minus z sub k. Right? You remember that the principal part, right? It's this. You can write this thing as a as a power series starting from some negative power, and this is the start part from 0 onwards, and this is the negative parts. Right? Okay. So so this is right. Right. So you have the principal part, and then you have the holomorphic, the part that's holomorphic in some neighborhood of z sub k. Okay, and then you do something similar for the infinite part. So for infinity, you look at f of 1 over z. Okay, right. This is what we call f of well. You look at f of 1 over z and write it as call it f infinity z plus, I'm sorry, f twiddle infinity z plus g twiddle infinity z. So again, these are the principal and holomorphic parts near 0, right? So so again, this is the principal part. This is a polynomial in 1 over z, and then this thing is holomorphic in some neighborhood of 0. Okay. Okay. So, and then what you do is you say, well, let h Okay, so then you say, well, let's subtract all of the principal parts to get rid of all the poles. Okay, so you say let h of z be your original function, subtracting off. Oh, I'm sorry. Then let f infinity z be f infinity tilde 1 over z. Okay, so we're flipping it back to infinity. So then we want to subtract that part off from our original function to kill the pole in infinity. So you subtract off that, and you subtract off all the principal parts for the finite poles. Okay. And you notice that when you do that, when you subtract off these things, you're not introducing any new poles, right? Because what you're doing is you're adding on, you're subtracting off a polynomial in 1 over z minus z sub k, right? That has no poles anywhere. The only pole that will affect is the pole at z sub k, right? So that you're not introducing any new singularities or anything like that. And in fact, as z goes to infinity, what happens to this principal part?
Goes to infinity?
Nope.
Or
It vanishes.
It vanishes, right? Because as z goes to infinity, this is just a finite polynomial in 1 over z minus z sub k, right? So everything's just going to go to 0, right? So it doesn't affect any finite pole, nor does it affect the infinite pole either. Yes, no.
Like for the principal part, isn't that only necessarily defined in a neighborhood of our pole? So how are we now subtracting it from our f like globally?
We're subtracting the function globally, and that's killing off the behavior locally.
But like, isn't the principal part only like there you have written that the principal part is only holomorphic in some neighborhood of z to the k,
Yeah.
or is only necessarily holomorphic.
Yeah.
So
this expression is only valid locally, but that's okay, right? This expression, this equality is only valid locally, but this expression you can define on the entire plane.
Okay. I
Right,
see.
and we subtract off that expression on the entire plane. The effect of it, it doesn't cause any trouble anywhere, but it gets rid of the pole at that point.
Oh, I see. That makes sense because the pole is just a polynomial of that thing. So it's
Exactly.
definitely a
So we just like
function.
subtract it
Okay,
off.
cool.
Yeah. Okay. So we subtract off, right? So yeah. So what happens then is that when you look at this h sub z locally, then it looks just like this. You're locally, this part is killed off, right? And you're just left with the holomorphic function, right? And so that tells you that the singularity is now removable, right? So this thing, the effect of this is that all of the z sub k become removable singularities. Right? Because you've subtracted off that thing. And similarly, the same thing, right? This is a polynomial in 1 over z, right? And when you subtract things off, you're only going to affect the pole when 1 over z is 0, right? Right. So in any case, you get rid of the pole at infinity. So this makes infinity a removable singularity also. Okay, so what's the end result? The end result is that h is a holomorphic function on the entire plane, right? It's a holomorphic function on the entire plane, but better than that, because infinity is a removable singularity, the function must be bounded, right? So this part gives you that it's an entire function, right? When you lose all the singularities in the finite plane, it's an entire function, and then the second part makes it a bounded function. So it becomes a bounded entire function and thus constant. And that's constant, right, by Liouville's theorem, right? So what does that tell you? That tells you that h is a constant, so f is just a sum of these principal parts plus a constant, right? In other words, it's a rational function. Right? So f must be, this thing plus these guys plus some constant. Right? In other words, it's a rational function. Yes.
And so all meromorphic functions, or all meromorphic, all functions that are meromorphic in the extended complex plane are completely characterized by their poles.
So yeah, that's this comment right afterwards. They say, look, if you have two such functions and they've got the same zeros and poles with the same multiplicities, then they must be multiples of each other, right? Because, right, so if f and g have the same poles and zeros with the same multiplicities, well, that tells you that the ratio has no zeros and poles, right? So this is that tells you that this thing must be a constant, right? That this thing must be a constant. Right, because it's going to be right. So this is on the extended complex plane. Right, because then what's the point? Sorry, it's going to be holomorphic on the extended complex plane. Right, being holomorphic on the extended complex plane would mean that you're a bounded entire function, and so it must be constant. Sorry. Right, because the point is that you're going to be holomorphic at infinity also, right? And that means that you're going to be bound. You're going to be bound. You know, one, you're going to be bounded in some neighborhood of infinity, and of course you're bounded outside of that neighborhood because that's a finite disk, right? So you're a bounded function, and so they must be constant.
At the beginning we said if f is meromorphic on the extended complex plane, then f of 1 over z has either a pole or a removable singularity at z equals 0. Why do we know one of those two must be true?
Because if you're meromorphic on the extended complex plane, that means you have at most a pole. It means you have at most a pole at infinity, right? Which means that f of 1 over z has at most a pole at the origin.
Right.
Wait, say it again. I'm sorry. I think.
No. I think you got it right. What I was asking is like, why? I guess like why couldn't? Is there an even simpler case we'd have to account for? Like, what if there's nothing going wrong at f of 1 over z when z equals 0?
Oh, I mean that's even better, right? Because then, right. So what we're trying to show is that f is holomorphic outside of. What we're trying to show is that f is holomorphic, close to infinity.
Yeah.
Right. Right. So if we have a pole at infinity, that means f at 1 over z has a pole here. But that means that it's holomorphic in that punctured disk. You invert the punctured disk, that gives you the place it's holomorphic here. Right? If you're holomorphic on the whole thing, then when you invert that, you're still going to be holomorphic here.
I see. Right?
In either case, you're holomorphic here, and thus all of your poles must lie in this finite disk.
Okay. Well, so I'm not sure if this example holds what I was thinking. What if f over z is constant, like f equals c? It's meromorphic on the extended complex plane, right? And our result is trivial, but f of 1 over z has neither a pole nor a removable singularity at z equals 0, right?
Your function is constant, right?
Yeah. Okay, maybe I'll talk.
Your function is constant, so definitely it's a removable singularity here. Right? F of 1 over z
Yeah.
is just going to be that 1 over that constant, right?
Yeah.
And you can extend it. You can extend it through that through the origin.
Yeah, I just thought it wouldn't have a singularity at all at z equals 0.
That's true.
Okay.
That's true, but what we're hoping to show is that we've got finitely many poles, and definitely we have finitely many
Okay,
poles.
gotcha. Thank you.
Yeah, so that's like even better.
So if you don't have anything wrong happening with f of 1 over z, then you must be bounded on the entire.
Yes, right? Because well.
It means you'd be bounded close to infinity, but you might have like 1 over a polynomial.
Yeah.
So you'd have poles elsewhere.
You might have.
just-
You might.
Yeah. Okay. 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 So that's all we wanted to say about that. Okay. So now we're going to do something called the argument principle, which has some really nice applications. Sort of a extension of application of the argument principle itself is kind of an application of the residue theorem. So here it is. Yeah, this is a very kind of powerful tool. Okay, so you have a function that's meromorphic on some open set. And as usual, you have some C, a circle in omega, with interior also in omega. Okay. So if f has no poles or zeros, on that path, then when you integrate 1 over 2 pi I of f prime over f over the path, what you get is the total number of zeros minus the total number of poles counted with multiplicity. So this is number of zeros with multiplicity. This is the number of poles, again counted with multiplicity. Okay, so that's the statement, and the proof is actually really straightforward. The proof relies on the following observation. So first, observe that if you have a bunch of functions and you take their product, and you take their derivative, and you divide it by the product, then what you get is the sum of the derivatives over the derivative of the function over the function. So this is a simple exercise if you want to do it. So do by induction. Okay. So okay. So now let's get to the proof. So you say, well, look, suppose we have a 0. So say that z naught is a 0 of order n, right? In that case, you know that f of z looks like z minus z naught to the n times some function, right? G of z nearby, right? But in that case, when you take f prime over f by the observation, you get this prime, right? So you get n z minus c naught to the n minus 1 over z minus c naught to the n plus g prime over g. Right, and remember that g was non-vanishing and holomorphic near z naught, in some neighborhood near z naught. Okay, right. In other words, we get n over z minus z naught plus some holomorphic function. Right, we get this thing plus some holomorphic function. Right? In other words, this thing has a residue of n. Right? So what does that tell you? That if we have around a small circle, right? If we take a small circle around z naught that doesn't have any other zeros inside of it, we get that this thing is going to be n. Let's C sub epsilon. C sub epsilon. Epsilon. C sub epsilon. Okay. So that just picks off, what is that? So integrating this thing picks off the number of zeros that zero gave you. Right? It was n zeros stuck together. And similarly for poles, if you do it for poles, you're going to get negative n. Right? So so similarly, z naught pole implies that f prime over f is going to be negative n over z minus z naught plus some other function, some holomorphic function. You do the same thing. The residue is negative n. Okay. So right. So if you have then you have your disk and you've got a bunch of zeros and holes inside here, right? You play the same game as usual, right? You put little as long as you've got a finite number of zeros and holes inside here, you surround each of them by some disk, and then you see that the integral of the disk, the integral over the whole disk, the outside disk, is going to be the sum of the integrals over the little guys. But that's just going to give you the total number of zeros minus the total number of poles. Right. You do some sort of keyhole argument. You make some passage, because you make some passage, right, et cetera, et cetera. Is that clear? Is that all right? Any questions? Okay. Okay. So I think we probably have time to do one more thing, which is called Rouche's theorem. Okay. So it says the following. So you have given F and G that are holomorphic in some open set omega, and as usual, you have a circle. So omega contains C, the circle, and its interior. The inside of what's inside the disk. Okay. If one guy is strictly bigger than the other guy, no, if F is strictly bigger than G on that circle, then F and F plus G have the same number of zeros inside C. Okay. Actually, this function can be stated for meromorphic functions, and in the case of meromorphic functions, as you expect, they have got this same difference. The number of zeros minus the number of poles will be the number of zeros of one will be the same as the number of zeros minus the number of poles of the other. I don't know why Stein doesn't do it in that case, but it's true. Okay. Okay. So proof goes as follows. What you do is you create sort of a way of sort of morphing one function into the other function. So define a family of holomorphic functions f sub t. So t is going to range from 0 to 1, and f sub t is just going to be f plus t of t times g. Oops. Okay. So right at time 0, when t is 0, you get f. Right. When t is 1, you get f plus g. Okay. So you're just linearly moving from one function to the other function. Okay. So let's observe that if you look at the absolute value of f sub t, well, that's the absolute value of course, this. Using the other side of the triangle inequality, you can get that this is bounded from below by the difference of the magnitudes. Right, as t ranges from 0 to 1. But we're already given that f is strictly bigger than g itself, right? So this this difference here is going to be positive, right? This difference is going to be positive because like, even if we subtract off all of this thing, we're still going to be positive, right? So this is right. This equals this minus this, right? Which is bigger than or equal to this minus this, which is bigger than 0 by assumption. What's the point? The point is that this thing is not 0. Okay, that's the main thing. that this thing is not 0. Okay. So so now you say, well, by the argument principle, we know that if we take the integral of ft prime over ft over the curve, that's going to be the number of zeros of ft inside C. Right? That's the number of zeros. Yes.
By the theorem statement, isn't it true that f can't have any zeros?
I'm sorry?
By the theorem statement, isn't it true that f can't have any zeros?
That's true, yeah.
Okay.
Yeah, f won't have any zeros. That's true.
Okay.
No, sorry. That's f won't have any zeros on C.
Oh, on C. Okay.
On C.
Cool.
Yeah, it's okay. that would sort of invalidate a lot of the use of this theorem. Yeah. Okay. So what's the point, right? That this is the number of zeros inside of C, right? Okay. But notice, because of the continuity of f so that's fine. Is that do you guys feel that that's appropriate music? Yeah, maybe
I don't know how to close the door this time.
you have to be more violent.
Oh my goodness.
It's like maximally distracting.
Okay.
Perfect.
So what's the point? The point is that this expression depends continuously on t. Okay. This expression depends continuously on t because of the continuity of the integrand. Okay. And further, it takes on integral values, right? And the right-hand side takes on integral values. Or actually, integral values. So because it's continuous and takes on only integral values, it's constant. Right. So it's constant. So that means that the number of zeros of when t is 0 and when t is 1, right? When t is 0, right? So f0 and f1 have the same number of zeros. Which is what we wanted to show. Yes?
Doesn't this show they only have the same number of zeros inside the disk?
Yes. Was that what I believe that's what we were trying to show.
But inside the disk, f can't have any zeros.
No. Remember what we said earlier. It's on the disk that f can't.
Oh,
have
on
zeros.
the okay.
Yeah. So
on the disk. Okay.
So on the boundary.
On the boundary.
Right, because you're saying, look, we know that this is bigger than that.
Oh, okay, cool.
So that's only true on the boundary.
Okay.
Yeah. So as for cool, I don't know, for a nice application of this, here's kind of a nice application. Take an arbitrary polynomial. And let f sub z be just z to the n. Okay, we're going to call this thing g of z. Okay, so P is our f plus g. Okay, so for large enough R, if we look at if we let C be just the boundary of the disk of radius r, we know that the absolute value of f is going to be strictly bigger than the absolute value of g, right? Because this z to the n is going to increase. This is going to, as n goes to infinity, this is going to increase faster than that, right? So at some point, we're going to find a disk large enough that this is strictly bigger than that, right? And so, what does Rouche's theorem tell you? It says that that P and F have the same number of zeros, right? In other words, that any nth degree polynomial has to have n zeros. This is another proof of the Fundamental Theorem of Algebra. Okay, that's it for today.